Okay, so let's look at acids and metal compounds and how they react. You need to know a lot of reactions with acids. Acids form an integral part of chemistry, so it's no surprise that they appear in various different reactions. So let's look at the first one. So metals reacting with acids. So we've got metal plus an acid will produce salt plus hydrogen. So this is just standard equation. You may have seen that at GCSE. You certainly need to remember at A level. And here's an example. So we've got calcium metal reacting with sulfuric acid, forming calcium sulfate and hydrogen gas. And we also need to know our ionic equations as well. So ionic equations, all we do is remove spectator ions from the aqueous solution. A spectator ion is something that doesn't get involved with the reaction in terms of it doesn't produce anything which is valuable, necessarily valuable to us. So, for example, you've got calcium and sulfuric acid, calcium sulfate and hydrogen. So the integral parts here are calcium, because there's the ions there, and the hydrogens, because that's what makes it acidic. So H plus, and that'll form H2. Clearly, the sulfate ions in there, but the sulfate doesn't change from the left, it doesn't change to the right, so it's exactly the same. So we call that a spectator ion. It's there, it exists, but it doesn't actually form an integral part of the reaction. So metal oxide plus acid will form salt plus water. Okay, so we treat a metal oxide as a base because it is a base, that's why. So we form salt and water. So an example would be magnesium oxide, which is a metal oxide, plus hydrochloric acid, which is your acid, will form magnesium chloride and water. So this is your salt that's being produced. And again, we write our ionic equation down. Our ionic equation shows us that we have MgO, which is a solid, H plus from HCl, and then we have MgCl2 and H2O. Now you'll notice here that we haven't split MgO. The reason why is we can only form ions which are in solution. So because magnesium oxide here is a solid, we can't split it into its ions. So anything that's like water, which is liquid, or solid, must remain as it is. You can't split them up. The only things we can break apart into ions are anything which has AQ next to it. So they're aqueous substances, so anything dissolved in water. So that's why the chloride bit here and the chlorine here is there's no difference there, there's no change there. Whereas from the magnesium there is, we're going to form an Mg2 plus, and obviously the water is produced as well. But again, we don't split water for that same reason. Okay, so let's look at metal hydroxides. Metal hydroxides react with acid to form salt and water. Again, they're very similar, they're a base. So for example, sodium hydroxide reacting with sulfuric acid will form sodium sulfate and water. And the ionic equation, they're all aqueous, so we can all split them all up apart from the water. So OH minus is the integral part here. The H plus is the most important bit here, and this bit forms water. So effectively it's a neutralization reaction. So we've got OH minus and H plus. Okay, so metal carbonates, again these are bases as well, but the difference is that this produces carbon dioxide as well. So we produce salt and water, but also carbon dioxide. So an example would be lithium carbonate reacts with nitric acid to form lithium nitrate, carbon dioxide and water. So you'd see fizzing with this reaction. The ionic equation would be H plus. Again, we split that. The nitrate is the spectator ion. It hasn't changed left and right. It's exactly the same. And then we form carbon dioxide and water. Remember, because these are not aqueous, they still go into the equation, but we don't split them up. For example, we don't split water up into OH minus and H plus because this is liquid. Okay. Conjugate pairs. So, a conjugate pair is linked by the transferring of a proton. Okay, so basically what we're doing here is we're following the proton. Where is it coming from and where is it going to? And we pair their molecules up. So any species that has gained a proton is the conjugate acid, and a species that has lost a proton is the conjugate base. Okay, so this is not to be confused with a standard acid. So for example, an acid is a proton donor and a base is a proton acceptor. So a conjugate is the opposite of that. So Bronsted-Lowry acids and bases, they react according to the following equilibrium. So we've got HA, which is your acid, B, which is your base, and that forms BH plus and A minus. So this is the general acid-base equation that you've just seen before. All we're doing is we're putting it into simplified letters instead. So HA is an acid in the forward direction as it donates a proton. So remember, that's what we said there. A minus is a base in the reverse direction, so that should have an E on the end. So in the reverse direction, as it accepts a proton from BH plus to form HA. Yeah, so there it is there. So there's the A minus. So that would accept a proton to form HA, which is here. So that is classed as a base because it would accept a proton to form that. Remember, this is a reversible reaction, so it can go forwards or backwards. So we have a conjugate pair with HA and A minus. So there you have a conjugate acid, which is HA, and your conjugate base is A minus. So we also have a conjugate pair with B and BH plus. So the conjugate acid is BH plus because that's the proton donor, and the conjugate base is B. So water reacts with acids to form H3O plus, which is the conjugate acid, and it reacts with the base to form a conjugate base, which is OH minus. So we've got to be aware of that because you'll see that quite a lot, and you've got to be careful that sometimes something might be called an acid in its name, in its common name, but it might not behave as an acid. What you've got to remember is that for anything to be an acid, it must donate a proton, and anything that is a base must receive or accept a proton according to the Bronsted-Lowry theory here. So you just got to keep that in your mind, and that's what you're looking for. So here's an example. So a base, for example, with the water. So a base reacts with water to form BH plus and OH minus. So this is the effectively the base is the B bit here is actually acting as an acid because it's accepting a proton to form BH plus. Whereas here, HA, which is the acid, reacting with water, water acts as an acid, water acts as a base because it's receiving that proton, and HA is acting, HA effectively is breaking up to form A minus. Okay, so let's look at acids and bases being strong or weak. So what we've got to distinguish, and what you've got to be able to do, is distinguish between weak acids and strong acids. So when weak acids and bases react with water, they form a reversible reaction. So acids, for example, if we react an acid with water, we form H3O plus. Remember, that's your hydroxonium ion, and A minus. That can be represented as just H plus. And a base will react with water to form BH plus and your OH minus, and that's what makes something basic. Strong bases dissociate or ionize readily. Okay, so they pretty much dissociate completely. In other words, a strong base such as sodium hydroxide will, when you add it to water, it will break up into its ions, which is Na plus and OH minus, and it will do that really easily. Weak bases won't. And likewise with strong acids, exactly the same. So strong acids dissociate really well. So for example, hydrochloric acid, HCl, the HCl breaks up readily in water to form H plus and Cl minus ions. There's very little HCl molecules left, and you see them in the examples in this table. So a weak acid, these are normally organic acids, so things like ethanoic acid and other carboxylic acids that fall into that category. Anything with COOH on the end. The backwards reaction is favoured in these types of reactions, so we don't get many H plus ions produced, and you'll see in this reaction here. So in this case, we're using ethanoic acid. In terms of equilibrium, it lies well over to this side, which is the left-hand side. So we don't get much of these ions here, which makes them a weak acid. Okay, so strong acids, on the other hand, they are strong because they dissociate readily. So hydrochloric acid, sulfuric acid, nitric acid. The forwards reaction is favoured strongly in these types of reactions. So this breaks up readily to form H plus and Cl minus ions. Strong bases, these are such as sodium hydroxide and potassium hydroxide. These are classed as strong bases. Equilibrium lies well over to the right hand side here. So the strong bases dissociate readily, produce lots of these ions here. There's not many of these left, if any. Weak bases, ammonia is a classic example of a weak base. The backwards reaction is not favoured. The backwards reaction is favoured heavily in terms of ammonia. So in other words, we have lots of this on the left hand side, not so much of this on the right hand side. So because we don't have much OH minus ions, therefore it's classed as a weak base. You need to be able to, so those are your strong bases, strong and weak bases, and there's your acids. So you need to be able to identify and categorize different acids and bases in terms of strong or weak, because that's going to have a big impact on what type of reactions and what type of chemistry you're going to be looking at. So you must be able to remember